So today, I'll be going over the AP Calculus BC FRQ from the year 2016, number 4. This question focuses on two main concepts, the first of which is L'Hopital's rule, and the second is Euler's method, which I'll be going over in my presentation. So this question tells us to consider the differential equation dy over dx equals x squared minus 1/2 y. Part A asks us to find the second derivative in terms of x and y. Now realize that the second derivative and the first derivatives are in terms of x, which means that when you derive y, you have to use dy over dx and not just the value of 1. All the derivatives are in terms of x, so deriving y for the second derivative should give you a dy over dx. So the second derivative is equivalent to 2x minus 1/2 of this derivative, dy over dx, which is equivalent to 2x minus 1/2 of quantity x squared minus 1/2 y, taken directly from the dy over dx in the given equation. Now this question is worth 2 points, and both points are given if you end up at the correct second derivative value. So part B tells us to let y equal f of x be the particular solution to the given differential equation whose graph passes through the point -2, 8. Does the graph of f have a relative minimum, maximum, or neither at the point -2, 8? Justify your answer. So first and foremost, we have to determine if there's even a possibility of having a relative minimum or maximum at -2, 8. So we plug in -2 for x and 8 for y into the first derivative to find that it's equivalent to -2 squared minus 1/2 times 8, which is equivalent to 4 minus 4, or 0. So now, knowing that the first derivative is 0, we can go into the second derivative, which we solved for in the first part of the question. Or we take the second derivative from part A, which is 2x minus 1/2 quantity x squared minus 1/2 y, and plug in -2 for x, here and here, and 8 for y. And we get that that's equivalent to -4 minus 1/2 times 0, which is -4. And -4 is less than 0. Now we learned from the second derivative test that if the second derivative value at that point is negative and the first derivative is 0, then we have a relative maximum. If this is positive and this is 0, it's a relative minimum. But here, because -4 is, well, negative and it's less than 0, the graph of f has a relative maximum at -2, 8. This question is worth 2 points for the conclusion with the justification. Part C tells us to let y equal g of x be the particular solution to the given differential equation where g of -1 equals 2. We're told to find limit as x goes to -1 of g of x minus 2 all over 3 times quantity x plus 1 squared. Show the work that leads to your answer. So we start out by just writing out the same thing, and we plug in x equals -1. Plugging in x equals -1 gives you 2 minus 2, 0 in the numerator, and 3 times 0, which is 0 in the denominator. Now we recognize this as a L'Hopital's form. Here in L'Hopital's, then we can just do the L'Hopital's rule and take the derivative of the numerator and put it over the derivative of the denominator. Doing that, we find out that the limit becomes limit as x goes to -1 of g prime of x over 6 times x plus 1, which, plugging in -1, still gives you 0 over 0. Then, because you have a L'Hopital's form again, remember you can do L'Hopital's more than once if necessary, as long as the form keeps going to 0 over 0 or infinity over infinity or any L'Hopital's form. So because this is another L'Hopital's form, we can do L'Hopital's again to get limit as x goes to -1 of g double prime of x over 6. To get -2 over 6, simplifying to -1/3. This question is worth 3 points, 2 for knowing and using L'Hopital's rule, and 1 for the correct answer. So part D says to let y equal h of x be the particular solution to the given differential equation with h of 0 equals 2. We're told to use Euler's method, starting with x equals 0 with 2 steps of equal size to approximate h of 1. So Euler's method is essentially linear approximation over and over again. So what we're going to do is write an equation using x equals 0 and the slope given, because we know that h of 0 equals 2, which means that the x and y values are 0 and 2 respectively. So we plug that in to get the point slope form, which is y minus 2, or the value of y, equals negative 1, plugging 0 and 2 for x and y respectively into the dy over dx equation, or slope equation, given for this problem, multiplied by x minus 0, which is just x. So then we plug in x is equivalent to 1/2, as each step is an equal size, meaning that to get to 1 in 2 steps, from 0, each step has to be a value of 1/2. So plugging in x equals 1/2, we get that y equals 3/2. Now we have a new point, 1/2, 3/2 for x, y. From here, we can do another linear approximation. We create another point slope form using this 1/2, 3/2 as x, y. So we find that the next point slope form, plugging in x and y, 0.5 and 3/2 respectively, into dy over dx, to be y minus 3/2 equals negative 1/2 times x minus 1/2. Plugging in x equals 1 to approximate h of 1, we get that y is approximately 5/4. Thus, the value of h of 1 is approximately 5/4. This question is worth 2 points, 1 for knowing and using Euler's method, and 1 for the correct approximation. For extra practice with L'Hopital's, you can visit AP Calc Bc FRQ 2013 number 5. Keep in mind, there are plenty of other FRQs that include L'Hopital's. They're just not a specific question in there. It's a specific part of a question. Another great website to visit is Khan Academy. Go to their homepage, AP Calculus AB, Derivative Applications, and L'Hopital's Rule. There you will find great videos and plenty of practice problems. If you want extra practice on Euler's method, you can look at the AP Calculus BC FRQs 1999 number 6, 2005 number 4, 2010 number 5, and 2012 number 4. And if you would like extra practice or to look at some videos, again, you can go visit Khan Academy. Go to their homepage, AP Calculus BC, Differential Equations, and Euler's method. There, just like with L'Hopital's, you will find plenty of informative videos as well as many practice problems. Thanks for watching, and I hope you learned how to solve the AP Calculus BC FRQ 2016 number 4.